For today's seminar, what we want to cover a little bit is in the first seminar we looked at how you can use Photon Forge to do design of your photonic integrated circuit. But the other major part of doing photonic integrated circuit design is figuring out where to fabricate these devices, and then fabrication, choosing the foundry and designing for a particular technology stack does play a big role in how you design the devices. So we want to give you a sense of, what are the different things we've done to make that process very easy for you. Um, all right, so just kind of like a high level overview of a typical PIC design workflow. I mean, this kind of depends very much on what you're doing, but usually, you try to design a PIC because you're trying to achieve a goal, whether that's, building a photonic integrated circuit that goes inside a pluggable transceiver for or it's for a LiDAR chip. Sometimes you even design chips for test and measurement equipments, right? There are photonic integrated circuits inside. Or you're building more complex quantum systems that can scale easily with photonic integrated circuit. And typically you start with some sort of system design and analysis, trying to figure out, what is it that thing I'm trying to build. Um, you then also figure out, okay, if I were to, if I want to achieve this type of functionality, like, can I just achieve it with, you know, SOI platform? Or so there's a little bit of figuring out to achieve a given functionality, what components I need, and then where I can fabricate that. And then you go towards, okay, here are these components that the foundry already provides, but then there are some components that I need to redesign. So you quickly enter this kind of design cycle. And you might go back and forth. I haven't added a bunch of loops here. So this is a very iterative process. Once you do that and you've kind of come up with all the components for your pick, you do a physical layout, you look at PDKs, make sure like it follows all the design rules, do all the mask preparations, and then you've eventually send that to a fabrication house. You wait for a few months. I guess it depends on how long the fab cycles are. Typically can be in the order of several months to maybe even a year in some cases. You get those things back, and you do your measurements. In some cases, you might also need to package and put it in a system to see how actually the pick behaves, right? And then you take that data, you feed it back into your design and this cycle is usually iterative. And and even in the system design step, like identifying where to fabricate a device is a critical step in your design process. You might start with product specifications like speed, size, power, what type of yield I want. And then you say, okay, I might be able to do this with the SY platform, or let's say I need a very high speed modulator. Maybe I want to do it in tungsten lithium niobate, and so on and so forth. And once you choose that kind of the technology stack is what we call it, our process node. You then look at the foundry. You go talk to the foundry. You sign an NDA. You get their PDK, which has information about the processes that they use to design that particular chip. Right. It has some reference designs, also design rules. And you eventually feed that back into your system design, run maybe some circuit simulation, do some sensitivity analysis, and then you do this kind of iteratively. Um, Now, what's inside this PDK, right? That the Foundry gives you. And here I'm actually taking some screenshots from I think Cornerstone has their open source Foundry PDK. You can just go online and kind of browse through and look at some of their offerings. Um, And so typically you'll have some sort of process manual like that has layers and process flows, cross sections, like you can see here, material parameters, how to size and how to size your chips for dicing and fabrication tolerances. You'll also have some design guidelines, right? How to draw your GDS, in what layers, what are some of the layout rules? You might even have some doping and implant information, back end of the line processing rules, all these things. And typically, this comes in a PDF format. And there isn't quite a standardization yet, so it varies across foundries. And then the other really important thing that you get from, in a Foundry PDK is you also get the reference component library, meaning, the Foundry themselves have optimized some of these devices for you for a particular, let's say, 1310 nanometer or 1550, and you can use those to kind of base your design. Or you might say, here's a particular component I can already use, or there are sums that don't satisfy my requirement, and then I might have to do some simulation. Um, and you also, usually have either some sort of design rule checking package, whether that's in open source software, K-layout, or more like proprietary software like Calibra. So this is what we mean by when you say you get a Foundry PDK. And so in Photon Forge, what we've done is we've kind of done the hard work to kind of read through that PDK and really implement it in our software so that the process of for you to kind of go from maybe doing a layout or even just looking at the cross section and starting to do simulations is a lot faster. And that way you can kind of both validate some of these designs, but also, optimize and come up with new designs a lot faster and saving you, weeks of time. Um, and the idea is that when you use those Foundry PDKs in Photon Forge, you should be able to do a realistic layout. um, some of the key advantages that we offer through Photon Forge is that we have seamless access to our GPU accelerated solvers, and as you can see, we're building a lot more capabilities so that you can not just simulate one type of physics, but other physics like charge, heat, RF, and so on and so forth. Um, it's very easy to go from component simulations to circuit simulations, and for both frequency and time domain. And then we're also adding powerful layout capabilities. Everything is kind of done at the C++ level, even though we have Python, wrappers, because once you start doing very large layouts, speed becomes very important. And then we do have a growing Foundry PDK support. These are some of the ones. I think this is a little bit older now. We have support for more PDKs, and we're continually working with foundries to provide this offering to our customers. And we have built PDKs across very different material platforms, so that shouldn't be a problem. And overall, the goal for us in this kind of photonic design automation space is as the complexity of your photonic system increases. So here's an example of, increasingly we are starting to see, co-packaged optics architecture for a data center. um, there are going to be more physical simulations needed to build more complex models and to even create these abstractions between system circuit design and actually the component design. And so this is what we're trying to do to bridge this gap and make it very easy for you to design complex PICs. To dive in a little bit deeper, so how's the PDK actually implemented in Photon Forge? So we have implemented the PDK in a way that's very easy for designers to understand and translate that to other formats. You can also kind of modify and create your own custom process stacks. It's very easy to, everything is parametric, meaning you can change everything from the layer thicknesses to, material parameters. So typically a technology object, which you can think of essentially as a Python object, um, has layers and masks as some material parameters, extrusion specifications of how to how to basically build a chip layer by layer. There's some information about ports, meaning in any given technology, a foundry will typically recommend, okay, for this 1310 nanometer wavelength, here's a standard waveguide that gives you like low loss. And so by ports, we mean both for optics and also for electronics. And there's also information about tolerances, right? So you, and this is very important to account for, and we'll see this later in the second half of this presentation. We'll go through live demos, and we'll look at some notebooks. We'll run through them and see how we can do fab tolerancing in Photon Forge. But the idea is that all this work that we've put in means that from the perspective of a user using Photon Forge, loading PDK is as simple as loading any other Python library. You can once you import that PDK, you can kind of load different technologies because a Foundry PDK might have different variants. Even for that given process, right? So you can kind of load different variants. Like in this case, this is an open source PDK that we can do demos. Most PDKs are closed source and require NDAs, and it's not possible to do these types of tutorials. But there are some open source PDKs like this one, the SciEpic from Lucas Grotowski's group, and it can be used as an educational tool here. And everything is parametric, meaning if you want, you can always change these parameters. The other important piece is a component. A component is in Photon Forge can be anything from individual components like a grading coupler, or MMI, or it can be even hierarchical things like an entire in this case a micro ring resonator is a component, right? But this is just a hierarchical component. Or you can even have the full chip. You can also call that a component. But component essentially it can be either virtual and schematic. It can also be real in a sense that it has a layout attached to it. If it has a layout attached to it, meaning it has some structures and geometry, you can actually export it to a GDS file. A component also has ports, like kind of shown here, and ports allows you to send light in and out of this component, like just like how you would do in your real PIC. But there are different types of ports. You can have optical ports, electrical ports. You can have terminals. You can also have virtual ports, and we'll see how these types of ports are kind of important when we start doing kind of schematic driven flow. Um, the other key piece for a component is a model. A model is how you describe how to simulate this component, or how you describe this component. Models can be based on simulation. For instance, we can run an FTTD simulation on this grading and build a model for that. Or we can have some analytical. If you have a long waveguide, it probably doesn't make sense to do an FTTD calculation. So there are ways to do somewhat semi-analytical calculation to extract the S parameter for this device, right? You can also have models that are based on experimental data. You can take measure data, load it, and build models for it. So all of this is kind of supported within Photon Forge. Um, and so a PDK in Photon Forge is essentially, you can think of it as like a version controlled package, Python package, which has both the information about the technology. Technology itself is versioned. Technology that you can have multiple technologies within a PDK. Technologies are parametric. You can have components. The components can be either parametric or even just GDS files. So, for instance, you know, if you looked at that earlier Cornerstone PDK, it came up with a bunch of reference designs, and those are just going to be GDS, right? GDS files, and they may not be parametric. And in that case, you can have components that are just loaded from a GDS file. And then you can also have some data and for your components inside this PDK. And so the way we do kind of version control and management of our PDKs is that all the files here are you do change management through Git, and then we do version control at the package level, meaning once the Foundry PDK updates to a new version, we basically change things here, and then we release a new PDK version, and then a user would just do pip install a new, like let's say SciEpic with a different version. Yeah, so once you load PDKs, PDK components, you can either combine this with your custom designed components. We'll see this in shortly, and then you can either do kind of the schematic driven flow, meaning you just kind of, or also netlist driven flow, which is you just put, you just place your components, connect them, define just connections, and then use that to run circuit simulation. Or you can also do layout driven flow where you actually put your components, connect them, use that to build a netlist, and also run circuit simulation that way. One of the one of the things that we can do because we have a lot of our own GPU accelerated solver is to provide a very seamless way to go from 2D layout files to 3D electromagnetic simulations. And you'll see that we're this way you don't have to keep rebuilding the geometry over and over again in multiple solvers. Like if you're running it for a heat solver or RF simulation, they're all going to be kind of unified through this layout. Yeah, so here's an example showing that with the capabilities we've added now we can integrate with both RF and optical solvers, and you can also run electro-optic simulations. For in this case, it's a electro-optic simulation of to calculate the V-pile of a thin film lithium niobate modulator. So you're running both the RF simulation, optical simulation from one interface. And the other big piece, which is what we're going to talk about today, is typically you can combine all these individual components, run circuit simulation, and get design something complicated like a cascaded MZI filter here. But the other big piece is whether or not this will actually work when you fabricate it, and that has a lot to do with making sure that all the components that you've designed, you designed with kind of variability and fabrication variability into mind. And so we can do Monte Carlo analysis and parametric sweeps to kind of understand these, and we'll look at that later today. So in today's demo, we'll first start simple. Basically, we'll load and inspect PDKs in Photon Forge. We'll see how to like inspect cross sections, how to maybe modify the technology. We have a lot of resources in our documentation page to help you customize the technology. Um, if you're interested, we can also help you build. We've done this enough times now that it's pretty straightforward for us to do that. And we've also designed the whole PDK so that it's really simple. There aren't tons of files. And then the second part is we'll see how we can seamlessly go from simulating individual components directly from layout to actually do the schematic driven layout for a relatively complex circuit. In this case, this CWDM, and doing circuit simulation and also Monte Carlo analysis. All right. I'll quickly pause there. If are there any questions that need to be answered? If not, I can kind of move to the second part. That's so. What is the difference between Photon Forge, Tidy 3? Are there different structure things? That's a really good question. Actually, Photon Forge is you can think of it. It's more like the structures that you are loading in Photon Forge are more at the layout level, right? So 2D geometries, something something that you would actually send a foundry to do fabrication, right? You send GDS files. Tidy 3D structures are full three-dimensional structures, and Photon Forge essentially what it does, it builds you the Tidy 3D structure. So you can export your layout files very seamlessly with basically one function call to build the full Tidy 3D structure. And so the reason why you're able to do that is because the technology that we've built in Photon Forge already has all that information about all the extrusions and everything. But yeah, that's a really good question, and we'll see that here. All right. All right. So yeah. So let's get started. We'll do something. The first thing we're gonna do is something really simple. Where let's say we look at a technology. Let's say a foundry. In this case, SciEpic, because it's open source and we can kind of do these tutorials. And the SciEpic PDK is I think it's a SOI platform with silicon nitride technology. And the way we essentially import this PDK is just like we import different, Python libraries. Importing Photon Forge is also another Python library. Importing Tidy3D is another Python library. SciEpic PDK is also another Python library. And this is also how it's released. There are other things I'm importing here, but you can kind of ignore that. So now loading the PDK is as simple as saying, okay, scipic.ebeam. And you can see here that there are a lot of things that you can kind of customize in this particular eBeam technology. For now, I'm just loading all the defaults. And I can look at what I loaded, right? So you can already see this technology comes with a bunch of different layers. You can see it, silicon is silicon nitride. There's a heater layer. There's some doping layers, some layers for black box, and so on and so forth. Some layers for dicing. Um, and by looking at that PDF document, essentially, what we've done is we've also translated, by looking at the process and how things are built, like what happens to these different layers. So, for instance, the silicon layer here goes from 0 to 220 nanometers, and there's some material specification for that layer. You can see there's no sidewall angle on that layer. Of course, this is something you can easily change if your process is different. Typically, these are provided by the foundries. So the time where you need the place where you want to change this is when you are looking at variability, for instance, right? Um, you also have various ports. You can see, uh, there's a T port 1550 with the 500 nanometer wide waveguide. There's all sorts of other optical ports, and then it's also, this specifies what type of background medium to use. All right, so we've already seen the layers. So now what I can do is, I can build a very simple a component. Let me. Yeah, I just want to show you. So here, all I'm doing is, this is just layout manipulation, right? So I start with an empty component in Photon Forge. We saw this a little bit in the first part of the webinar, and then what I'm doing is basically saying, okay, let me add a rectangle to this silicon layer, right? And what this layer is in the GDS is defined already in the technology. So it's layer 10. I can add some rectangles for silicon nitride, silicon slab, silicon heater layer, so on and so forth. So here it just looks like a 2D layout file, right? Something that you would kind of give to a foundry. So if you convert this to GDS, um, this is what you would give it to the foundry. What we can easily do is you can look at that component and look at actually the cross section of that component, right? So you can see, okay, this is what this cross section is going to look like. Should be able to also do like a 3D cross section here. Um, I don't know, my internet here is probably not working very well. But yeah, anyways, so you can try both of these views, but the idea is that Photon Forge has enough information in the technology to go from these 2D files to 3D views and cross section. It's very easy. This is very helpful because you can already see. So this is the slab for the silicon waveguide. The nitride here is actually on the same layer as the silicon. There's some vias you can make to basically remove the cladding all the way down to silicon for this platform. There's this heater layer here, and there's the router layer, and you can also kind of etch down here to expose the metal. So this kind of cross section allows you to quickly view the PDK. Um, Another thing you can also look at inside a PDK is also what are all the variations, right? So here it's very just for simplicity, we've only added two random variables. For instance, the silicon thickness here is 220 nanometer, but there's some standard deviation. Also, the bottom oxide thickness has some standard deviation, and this these things are things that will be different for each foundries based on what they've specified and something you can also add manually to this list. The other part of technology file of a PDK is all the reference designs that the foundry already provides. So we can quickly look at those by just calling SciPic. What are the other components that are offered by this foundry? And loading them is as simple as saying SciPic component, and you just say, okay, so in this case, I'm loading a grating coupler. But if I wanted to load something else, let's say I wanted to load I wanted to load uh, a Y branch. So you can just put that in here. And you see this is a different component. And these components, typically the ones that are provided by the foundry, already come with ports and models defined for it. Of course, you can do a little bit better view than looking at it over there. Um, you can kind of visualize it here and kind of zoom in and okay, inspect like what's the, so for instance here the width, this is should be zero point 0.5, yeah, 0.5 microns. So that all makes sense. There are other components, right? Like the termination, for nitride termination. There might also be, black box components. Black box components are components where the foundry has only given you information about the ports and kind of they're hiding exactly what the geometry is inside. Um, Black box components typically should come with some models. Otherwise, it's not possible to directly simulate these because you don't know exactly what the geometry is inside. But this is also common. And in that case, you might want to build models based on measured data when you do circuit simulations. We'll look at a slightly different PDK. So here we also have another open source PDK, the Luxtologens thin film lithium niobate PDK. It's the same process, is you import it as a Python package. In this case, the way PDK has been built is that you can also choose to include the substrate or include the air above it. And the reason for making even the whether or not to include the substrate parametric is that for lithium niobate, for instance, if you're trying to do RF simulations, you do need to include the impact of the substrate, right? But if you're just trying to do optical simulations, you don't need your optical simulations would be too large if you were to try to incorporate the whole substrate and the air above it. So this is just to try to make it easy for you to select what types of structures are built when you go from your 2D files to 3D geometries. Again, this for this foundry PDKs, there's going to be different layers and descriptions for each of those layers. So in this case, the thin film lithium niobate slab is in the 3.0 layer, ridge is in 2.0 layer, and so on and so forth. There's actually a heater layer. There's also a transmission line layer. Same as before, we can just add a few rectangles on these different layers just to get a sense of what the cross section looks like. And you can see that you actually can etch all the way down to the to basically a box for in this particular technology. And for instance, this is helpful if you're trying to make a very good a low low coupling loss edge coupler. You have this metal layer above it. Here's oxide. This is air. This is the silicon substrate. So silicon substrate box. You have lithium niobate. You have a metal, and then you have air. So you can kind of quickly visualize what that cross section looks like. Of course, you can kind of go through here and look at the extrusion specification. You can see that this is a 400 nanometer thick lithium niobate. There's also a metal that's about zero point 0.9 micron thick. So yeah, you can use the extrusion specification to what materials are used. For instance, in this case, like lithium niobate is anisotropic, so there's an anisotropic medium definition for that medium. And you can also look at all the different ports that comes with this particular PDK. There's also electrical ports. So in this case, a coplanar waveguide with 15 micron signal, 5 micron gap, different widths and different very very different settings for electrical ports versus optical ports. Um, for Luxtologens, the PDK libraries are actually there's also parametric, meaning you can update these parameters if you were to, let's say redesign it for a different wavelength, right? So if I look at it, I can change the length, I can change and make it different. So if I were to do length equals 10, if I do this, this will be something else. Of course, in lithium niobate, because the refractive index is closer to the effective index closer to 2.2, everything is a little bit bigger, right, than for the SOI. All right. Yeah, you can load other things like directional couplers, and just like I was saying earlier, you can components. If you look at the type, this coupler, it's a component, right? Photon Forge component. This is an edge coupler. This is a dual, dual edge or double linear inverse taper edge coupler. And this is also this is a more complex component. There's a phase shifter. You can also have unbalanced MZI, which has a bunch of right. So it's actually a bunch of different components make up this larger component, and so you can but at the end of the day, even this big circuit with a bunch of components, if you look at the type, it's still a Photon Forge component. Right. And you'll see why this is important later on because no matter whether you're doing an individual component level S matrix simulations or S matrix simulations of a big circuit, it's the same function call, meaning it's just one line of calling S matrix. And this is what we mean by we make it very easy for you to go from individual component simulations to an entire circuit simulations. Um, Here we can look at a little bit of how you can modify the technology. So one of the things you can do is, okay, earlier the sidewall angle was D is 0. We can just load this technology and you can see that now the silicon sidewall angle is 1 degrees, right? Um, and then you can also change these extrusion specifications. So for instance, like earlier, we saw that the silicon nitride went from it was basically at the same level as the silicon layer. But let's say I wanted to move it up above, right? So then I can just take the silicon nitride extrusion specification and instead of it going from 0 to 0.4, I can just modify it. And you can add additional extrusion specifications, so on and so forth. If you add doping layers and whatnot, you can always modify this and to make it very easy for you to do that. And so if I were to now, I modified this technology and changed the location of silicon nitride, and I can just quickly visualize it. You see it's kind of moved up relative to what was in the PDK. So it's possible to really easily customize it. And if you go to our docs page, we have a lot of example libraries and help, but you can also, we have some notebooks to walk you through how to kind of customize and create your own technology, your own PDK. All right. Do we have any questions before I move to the part two of this talk? The way it's done actually is the way I think about building this PDK and building this extrusion specification is think of it as like you're building the chip layer by layer. So it kind of follows this order here. So if you look at the extrusion specification, the ordering here is what determines how things are prioritized. This is where you kind of do that. Oh, and yeah, so for simulating 3D component, especially for very complex one like ring and modulator on top example, how would you manage the meshing to make sure they're enough but not overly done? As I know, Type 3 has a hard upper bound for meshing that you cannot bypass, and will Photon Forge be constrained by a similar rule? Yeah, so any meshing rules, the constraints in Tidy 3D, we're gonna have to live with that. That being said, remember, I think the big advantage here with Photon Forge is that just like this, right? When I'm trying to simulate this very large component, I'm not going to simulate all of this at once. I'm going to simulate piece by piece. So the calculus here is a little bit different. So at the component level, you can actually mesh a lot, and then you can do this kind of combine these S matrices to do circuit simulations. You can do mesh overrides, and so it's internally it's using the same tidy 3D model. For PDK solutions, does Photon include some consideration in fabrication infrastructure various as a learning tool? Yeah, so the prefab we don't have the tools that can kind of predict given this GDS and given fab process something has been trained before and we don't have that because at least yet. I know there are already tools like prefab that you can use for that. That requires a lot of uh, it requires you to get a lot of data and maybe train models specific to every maybe layers and process stack, right? So it does that something building something like that takes a little bit of effort. And then that's really cool for us. So for example, I can use a SciPic PDK loaded in a Jupyter notebook to create a circuit simulated, then export it to GDS. That's right. Yeah, that's it. You can do that. That's the whole point of being able to load the PDK. All right. So with that, I'll move to what I think is the more exciting part of this webinar, which is really trying to design something very complex and also trying to make sure that this can be fabricated. Um, so I'll do the same boilerplate thing. I'm just loading the Python packages. I'm also in this case I'm just going to use the SciPic eBeam. Um, and then I'm gonna get everything set up here. But let me now explain what we're trying to do here. So this is from a paper by that was published in 2015 by Wim Bogaerts group, and you can see like what this is essentially a CWDM filter that's made by using a bunch of cascaded MZIs. And there's very specific design rules to achieve this kind of filtering behavior. So you need to combine one, two, three, four, five directional coupler with these very specific splitting ratios. So in this case, 50-50, 13%, 12, um, 50%, 25%, with these very specific uh, phase length, path length difference for these paths. And then with that, you're able to essentially come up with a lattice filter like this that has a, a frequency response with some given channel spacing to filter out. And then when you put these types of cascaded filters in this specific geometry, you're able to filter out the odd and even wavelengths. And then finally make a device where if you put four different wavelengths, it actually filters out each of these wavelengths into different ports. And this device is actually fairly big, right? And we'll see how we can design everything here in Photon Forge by using our connection with Tidy3D. All right, so here are the kind of desired power ratios we want to just build this section first. But even before that, let me just show you how easy it is to kind of run simulations, FTTD simulations from Photon Forge. Um, so for this, I'll actually slightly change this wavelength so we can actually see it happen live. Um, because everything is cached, so otherwise you wouldn't see it happening. So I'm just gonna use, so in Photon Forge we have a lot of we're increasingly adding more components to our component library, so you don't have to keep rebuilding these generic components. For instance, for this S-band coupler, you can just call we've already made this for you, and you can just call the S-band coupler, tell it what port you care about, and then what's the coupling distance, coupling length, so on and so forth. So this parametric component has ports already, and it also has a model. So if you look at coupler.models, it has a Tidy3D model, meaning that's enough for it to now calculate S matrix. And to calculate S matrix, it's a single function call. You just need to say coupler, which is this component, give me the S matrix in this frequency range, right? So if I do this, it'll actually run a simulation live. It's already running it. Should be able to. How do I hide this? Um, so it's already running this FTTD simulation. And so this is what it built, right? So Photon Forge automatically built this geometry, put all the right ports and so on and so forth. And then once this simulation is complete, we'll be able to and you see this simulation is we can kind of keep see the status. Oh, I think it's already done. So yeah, so you see the simulation ran really fast, and you already see the results. I'll go back to the other wavelength because a lot of these results are already cached, so it'll be easier to do this live. Okay, so you see that with this directional coupler gives you roughly, I would say around 85% splitting. So 85% coupling on this side. So the coupling coefficient would be around like 15% here. Um, we can actually estimate the cost if you're worried about running these models, but also just get the actual cost is only around 0.12 flex credits. Now this is where it's very important to run these variability studies right off the bat because you can take a look at this component and maybe if you're a photonic designer can already tell there's a lot of problems with this device. Meaning these coupling distance is very short and the gap is very small. So let's look at what happens if I were to just have a 10 nanometer standard deviation. So to do that type of study of how the fab impacts your design, you can run Monte Carlo simulations on your component. So all you need to do is instead of calling S matrix on the component, you just call Monte Carlo S matrix. You can tell what your component is, and you can define what are the parameters you're varying. So you can either, so let's look at it. So if I just say, okay, there's going to be some thickness variation across the wafer, and if I were to just give some values here and just run some, random sample, 6 samples with some 2 cornel samples and just see what you get, you can already see that there's some variability here, right? Um, and this becomes worse for other parameters, right? So if you actually just looked at in this case, it's coupling distance is really like the gap. So I'm varying, have a standard deviation of 10 nanometers. And you can see there's a lot more variability coming from just the gap being slightly different, right? And here, I mean, let's look at what are all the different gaps. So there's about, I guess it's sweeping in between 40. The extremes are about 40 nanometers different, right? And this, I think this is how, I think about things. So right off the bat for the component design, what you want to do is you want to combine all these different, things that could impact your device design and then update this design so that it's robust against fab variations. So how would you do that? So for this device, ideally what you would do is you would make the gap a little bit wider and then you just make the coupling length longer so it's less sensitive to the fab variations. So these are the types of studies you can do very easily in Photon Forge. Um, okay, so I've just quickly shown you how even simple fab variations like just changing coupling gap or we can even look at the sidewall angle. So with these types of study, you'll be able to do you're able to tell if what parameters affect your design the most. For instance, here I varied the sidewall angle between 0 to 5 degrees, and you can see that there is some variability, but it's not as bad as changing the coupling gap, right? And so you can kind of quantify these and then kind of update your design to make it more tolerant against fab variation. All right. You can also run entire optimizations in Photon Forge. This notebook has already been released, so you can run it yourself. Right now, I'm not going to go through that. So it's So there's a cascaded MZI optimization notebook. Um, I ask you to just, if you have time to just go through this on your own. Here, I'm just going to run through it quickly. Um, so I'm just going to run that notebook. And essentially what it's doing is we're changing the coupling length and we're looking at the splitting ratio. And then we're trying to pick what are the coupling lengths that's going to give me this coupling ratio, uh, these different power ratios that was mentioned in this paper, right? So that's all I'm doing. I'm just, these are just linear sweeps to extract these values. Um, Once that's done, as you can see here, you can kind of combine all these individual MZIs and basically you're doing this schematic driven layout to come up with a function, which in this case is a cascaded MZI, right? And I've just already ran this notebook, so it's already loaded. So this would be the first filter here. And as you can see here, this filter is fairly large. It's 212 microns long and 80 microns wide. So these are fairly large devices. You could actually in Tidy3D try to do this entire simulation using FTTD, but that would take at least like I think we've tried this before. It takes about 2 hours, and then also a lot of flex credit. Instead, what you can do is you can use circuit simulation, right? So we have already simulated all these components, and you can kind of again first filter dot tree view. Um, right? So we have all these components, individual components that make up the circuit. And what Photon Forge is going to do automatically now is because it's also a component and you can call S matrix function, it's automatically going to traverse this tree and figure out, okay, I've already simulated this device. I already know the S matrix for that. There might be some devices where I haven't done simulation, so it's going to automatically figure out what are the things that needs to be done to build the final S matrix model for this. So I'll do that. And in this case, I'm actually also increasing the wavelength, the resolution, so you can really see the see what that response looks like. So when you kind of put these different directional couplers with different splitting ratios and have different path lengths for these MZI arms, this is the response you get for this cascaded MZI, right? So you can already see there's some filter response, but to turn this into a four-channel WDM, you need to then uh, do something more complex, right? So you need to kind of stack them together and build this lattice filter. Um, as before, we can kind of inspect the different random variables, and then here I'm also the second filter is actually so with the second filter you're trying to so the FSR here is it's like 5, and then with the second filter you get a 10 nanometer FSR, and then that's how you're going to try to turn this two-channel cascaded MZI into a four-channel WDM, right? So I need to run simulations uh, um, for the second arm of the MZI, and you can see here this filter is actually fairly large, right? Zoom in. There's Okay. Yeah, so again, for the second filter with different path lengths, you can just call S matrix function, and a lot of these results have already been cached. So you see this happening really fast here. That does depend on a little bit on how many different simulations you need to run. Um, and you see now the FSR for this second filter is roughly twice, so 10 nanometers. Now this is the part that's very interesting, is to kind of see how just even variation in silicon thickness impacts this second, let's say this filter design, right? So all I did was I just took the silicon thickness and basically varied it, um, and ran some Monte Carlo simulations, and yeah, I can. But yeah, while we're discussing, we can see that when I plot these results against the original, you see that there's a lot of things are moving around quite a bit, because this is a fairly long component, right? So all these like slight phase differences kind of add up to shift your circuit. And hopefully this just emphasizes why it's so important to do these types of variational studies when you do your design, so that later on when you do a fab, you actually end up with a device that actually works. Um, right. So you can see we can even plot just like the first few. So you can see, okay, with a silicon thickness of instead of 220 nanometers is 214, you can see it's already shifted a little bit, right? If you look at a few others, there's a lot of variations from those. And you can imagine if I were to, I was testing this with just the coupling distance, the kind of variability you don't even see this cascaded field ring response anymore, right? So it's really important to do these types of studies. Um, okay, so the last part here is we can now take these. Oops, sorry, I'm moving quite a bit. We can take these individual cascaded MZI cascaded MZIs and then turn it into a lattice. Here we're doing netlist driven layout, meaning we just place these components, right? So we take three of these filters, one, two, and three, and then we place them at certain positions in this layout, and then we define routes. In this case, we have automated routing in Photon Forge to just say, okay, I want to connect port two of the first filter with port one of um, of the second filter here. And then for the model, we just say, okay, use circle model to simulate this device. And then here's the cascaded lattice filter. Again, when you do this type of schematic driven design, the thing that you end up with is again a Photon Forge component, right? And with Photon Forge component, calculating S matrix, there's no extra work. You just say lattice filter S matrix, and then it will calculate the S matrix for you, and you can plot the transmission spectra. There's actually quite a lot of data being loaded here. That's why it's taking a little bit of time, but you can see now we have this nice response for this lattice filter. You can do the same thing, same process, repeat, rinse and repeat for the second lattice filter. And this is what you get. Now, this is the part that's also, very important is you either load like PDK components or be able to specify models for your components based on, let's say, measured data or measured you have some touchstone file for your S matrix. You can just load that, you can create a data model, and then here I'm assigning this data model to this grading coupler component, right? So I basically loaded the grading coupler from SciPic PDK. I've loaded some S matrix and then created a data model based on that. And we can quickly plot what this kind of spectrum looks like, right? So if I just plotted the transmission spectrum, or that's a reflection spectrum, you see there's a losses, let's say about 4.5 dB for this. Um, and then you can also look at the full spectrum. Once you've created a you've loaded a grading coupler, which is, let's say, from a PDK, and defined a data-based model for this thing, you can now again do the final. You can create the final chip where you combine these different lattice filters again using schematic-driven layout. You can run the circuit simulation again at the for this lattice filter, and then finally you can combine this full chip with the grading. So later on when you want to measure these devices, right, you're gonna put these gratings at some spacing. So a typical fiber array spacing is 127 microns. So you're gonna put these gratings, you're gonna put that full chip design for the lattice filter, and you're gonna just connect them. And you can use some auto routing. You can define guide points, so you can do a little bit of nice layout here. And with this, you end up with this final circuit with uh, one input port and then four output ports. And again, because this whole thing is just a Photon Forge component, you can just run S matrix on this whole thing. And then now you should see a transmission spectrum that's also, the transmission spectrum that's also modulated by the grading coupler transmission function, both at the input and the output. So about somewhere around let's say minus 14 or 15 dB of loss, and you can kind of see the spectrum. And finally, you can take any of your Photon Forge component and convert it into a GDS file. Okay. GDS file, and you can also, it should create this GDS file, pic.gds. And you can also viewer. And then you should be able to see the entire design here. Right. And everything here should be all connected, and that's something that we can be certain about when we do these types of schematic driven layout. I think that's it for this tutorial series. If you have any questions, just let me know, and then we can make these notebooks available to you.
Uh, yeah. Sorry to interrupt you, Prash. There is a great question, so maybe you can answer that publicly. So, question is, do we need to sign NDA with all those mentioned foundries like Tower, AIM? And yeah, I think it is good because you can talk a little bit about so when we should pay attention to when using the PDK foundries.
Yeah. Yeah, absolutely. I think, yeah, you as a user, you always have to sign NDA with the foundries. We also have to send NDAs with the foundries to get access to their PDK, and then we actually, typically the foundries are the ones that release this package for you. We built it for them, and then it's released by the foundries as well. And yeah, just just let us know if there are other foundries that you guys are interested in, and we can also expand support for that. But yeah, you do need to sign an NDA with the foundry. Is it possible to include variability in measured data models? Um, yes. So the way it works, let me just quickly explain here. So the the data models themselves can be parametric. So you can if you have measured data for different, let's say, coupling gaps, uh, Photon Forge, when it runs the circuit simulation, will just call that, and you can actually take interpolated data and build your data. So if you have, if you actually have measurement for two different gaps, and then you build a function, an interpolated function, then in Photon Forge, when you run circuit simulations, as long as that parameter is defined in your component, you will pull the right data model for the circuit simulation. So yes, you can do that.
Okay, thank you, Prash.
Yeah, so for Monte Carlo, what you do have to do is, let's say you change the silicon thickness, right? So you would have to rerun, because you have to recompute the S matrix for, let's say, even the individual directional coupler, and you would have to do this at many places. So sometimes, let's say, for example, in that particular MZI, the long waveguides are actually simulated not using FTTD, for instance. They're simulated using what we call waveguide model or semi-analytical model. So when you change let's say, the thickness, you would have to rerun the mode solver simulations again automatically, and then recompute the S matrix for that. But the good thing about our GPU accelerated solver is that first, individual simulations are very fast, but second, you can submit like a batch jobs, right? So everything is submitted as a batch, so everything is a lot faster because of that. So it really leverages the GPU acceleration, the ability to run batch simulations, all that stuff when you try to do these Monte Carlo simulations. Yeah, so I think that's a good question. Try to better understand Photon Forge. What is the most? I think the big part here, as you can already see, is kind of is there's a couple of things, right? So first is like being able to load the PDK and directly do design there on the layout level. There's also this kind of coupling between device simulations and circuit simulations. Uh, so there's a lot of manual process when you start building geometries at the tidy 3D level. Um, and there's also a lot of analysis you have to do at the system level. For component level, that's true. But once you start doing like component design, like more like active device design, there's a lot of different things that you know, running RF simulations, optical simulations, that's a lot easier through Photon Forge. Yeah, PDK management. Uh, yeah, there's a lot of things that are kind of being able to run, like, let's say, go from layouts to 3D simulations. You can also follow the other workflow with Photon Forge, meaning you can start with component simulations. You generate S matrix, and then you can basically load that in Photon Forge to do your circuit simulations too. So it offers like different capabilities, even for component level optimization.